The fifth part of this tutorial deals with regenerative physical layer design. That is a fairly large section, so I will have to rush through a few slides, but you're welcome to pause the presentation and to read each single bullet point. Again, there are many contributions available today on the regenerative physical layer, and we will hence concentrate on 4 topics. We will deal with distributed spacetime block code design and analysis. We will deal with the estimate and forward protocols, with the decode and forward protocols, and also with the asynchronous protocol design. As for the distributed spacetime block codes, we have the following system model. At the transmitter side, we assume there will be T distributed transmit antennas, which transmit a spacetime block code word X. We also constrain the total transmission power of that code word. The channel is supposed to be frequency flat and uncorrelated, and we assume that each of these channels is represented by a channel HIG. All of them are grouped into a channel matrix capital H. At the receiver, we hence receive H multiplied by X plus N, where N is the noise with variance N per entry. As for the cooperation, if there happen to be any, we assume to be an error-free communication channel. Following 75, we assume a cooperative spacetime block code. That means if we go down to the figure here, we have an information source sending a signal S. That is being picked up by the T distributed antennas, where each of them may have an antenna, more than one antenna element. They hence realize a fractional spacetime block code and transmit it via that channel H here to the distributed receiver, which is the distributed spacetime block receiver that is being fed in a spacetime block decoder, and finally the error detection is done. Now we assume that each subchannel realization H subindice IJ obeys Aghvami fading with an arbitrary parameter F. That means we may have different gains per subchannel, which reflects exactly the distributed deployment. We also define a variable U, which is the product between the transmit and receive antennas, which reflects the exact number of these subchannels H here. We also define gamma I to be the channel gain per subchannel, and we assume a normalization if we add up all these channel gains that they are equal to U, meaning the number of transmit multiplied by receive antennas. Also for reference, let us define these variables here. They are valid for PSK and for QAM modulations, which depend on a factor alpha, U being the product of transmit and receive antennas, and M being the modulation indice. We have the gamma function here, we have the Gauss hypergeometric function here, and we have the Apple hypergeometric function right here. Using these functions, we can now express in closed form the simple error rate of such a distributed link, which is given through a summation here. So we use the summation over these coefficients which I had given you before, where inside as an argument we have in place of alpha 1 over r, where r is the rate of the spacetime block code, gamma I is the gain of that subchannel, Fi is the fading parameter, Aghvami fading parameter of that channel, T is the number of transmit antennas, and S over N is the signal to noise ratio. That is multiplied by a coefficient K, which is expressed down here, which looks a little complicated but is fairly easy if you resolve it for a specific case. The sum here spans from 1 to the integer number of the Aghvami fading factor, and that sum here spans over all possible subchannels. If we look now at the performance for a scenario like that one, we have 2 fractional spacetime block codes here distributed, and one of them might be a little bit shadowed here, that link here, and we have then a spacetime block decoder and compare the error rates. which I depict here. So I depict the symbol error rate versus the strength of the channel gamma 1, which is that channel here. And whilst I increase the strength of gamma 1 from 0 to 2, I decrease the strength of the channel gamma 2 from 2 to 0. As we can see, if we just used one link here, that means in this case we use just link gamma 1 with increasing strength gamma 1, the symbol error rate goes down. If we had just link gamma 2 with increasing gamma 1, gamma 2 decreases, and therefore we have a symbol error rate which increases. If, however, we use a distributed spacetime block code word, we get a very stable and very low symbol error rate which remains almost constant in a certain region and therefore exposes a very high stability for this link. That might be quite useful for wireless sensor networks where you don't know where your wireless sensor network will fall if you have a random rollout. Let's move on to the estimate and forward protocols. And what we assume here, again following paper number 75, we have a source terminal here which wishes to communicate with the target terminal. Each of the terminal may have more than one antenna element, and they use adjacent terminals which also may have an arbitrary number of antennas to send losslessly the data to these adjacent terminals. They form a space-time coding unit here, which I call the virtual antenna array, or a VAA, which is then transmitted to the second VAA, where then these terminals cooperate or may not cooperate with each other, but they're just spatially close. They transmit it to the third one, etc., until we reach the target terminal. So we are interested now to define the end-to-end error rate for a topology like that, where we estimate and forward. That means there's no transparent relaying. We try to estimate the symbol which has been transmitted, for instance at this stage here, but we don't do a decision whether the packet or the symbol is erroneous. Therefore, the decision on the erroneous reception will be done at the target terminal, most likely with the help of a CRC, with a cyclic redundancy check. Now, to find the end-to-end error rate for such a topology is very tricky because it depends on a lot of factors such as the modulation scheme, the channel statistics, the average channel attenuations, the type of deployed spacetime block code, the way they cooperate the nodes, etc., etc. And you get a lot of interdependencies between the stages, which makes the analysis very tricky. Now, let me explain how we proceed. By means of that simple topology here, what we assume, we have a source terminal communicating with a target terminal via a virtual antenna array, which is given here, where these two nodes do not cooperate, and also these two nodes do not cooperate. So we would like to find what is the probability that an error occurs in that type of topology. Now let me proceed as follows. We assume first of all that we operate at sufficiently high signal-to-noise ratio so that if an error occurs, it is just a single error which occurs in the network. Let us assume that that error occurs in this link, in the link P11 here. Let me illustrate that by means of the marker. So we say there is an error right here. However, there's no error here. That means, since they do not cooperate, these two terminals, that this guy is going to encode a wrong spacetime block code, and this guy is going to encode a right spacetime block code. And the question is, what is the probability that that error propagates towards this terminal here? Because that branch is correct and that branch is erroneous. Now, at very high signal-to-noise ratio, things behave fairly linearly, and what we figure out is that the probability that this error propagates to this terminal here is equal to the strength of that channel here, normalized by the sum of both channels, this channel here and that channel here. Equivalently, if an error occurs somewhere else, you would calculate exactly the same way the error propagates. So therefore, the probability that an error occurs is simply the probability that an error occurs right here, plus the probability, let's say, that an error occurs here, multiplied by the strength of that channel divided by the strength of that and that channel, plus the probability that an error occurs here, multiplied by the strength of this channel divided by the sum of these two, etc., until you have all the topology included. What I've explained to you orally now here is given in that text here. You're welcome to read that. And if we summarize what I just said, you get an approximate end-to-end error rate, which is given through that term here. You can simplify that in this notation here. The C subscript VI is a probability that an error occurs in link VI. You can then assume also that some of these terminals actually cooperate. So we assume there's no cooperation, but you're welcome to assume that there's a cooperation and they form cooperative clusters. And let's assume we have at stage V, and there are 1, 2k stages, Q subscript V cooperative clusters, and then you can express the end-to-end bit error rate by means of that equation 39. We have simulated that case, and let me explain you the right-hand side graph where we depict the end-to-end bit error rate versus the signal-to-noise ratio for a 3-hop network. And we really varied the channel strengths of each of these channels arbitrarily and randomly, and they're very, very different. And as you can see, the expressions hold with a very high precision for the high signal-to-noise ratios. And as expected, because we assume that just one error occurs in the network for the high signal-to-noise ratio, if you do have a signal-to-noise ratio which is not that high, you do have a deviation from the theoretical performance. Also, those of you who are interested in 75, we derived the end-to-end throughput maximizing fractional power and frame durations. What has been done here is that, of course, if you do have different channel power gains, it is not optimum to allocate the very same power to each node. You therefore should allocate different power to different nodes, and also each node, each stage should transmit with a different frame duration so that you optimize the end-to-end throughput, and that has been derived right here. If you are interested in details, please consult paper 75. Let's move on now to the decode and forward protocols. And to this end, I would like to show you a few classes of decode and forward protocols. The first class is the repetition-based decode and forward protocol, where you basically repeat the very same code word during relaying. Meaning, you have a source terminal transmitting to the target terminal a set of data, which is that one here. That has been picked up by the relay, and he transmits exactly the same data to the target terminal. Now we know that repetition codes are not optimum codes, and therefore using channel code based relaying where you relay parity data performs better than the repetition based. What happens here, the transmitter transmits a certain code word that is being picked up by the relay, it decodes, it generates the parity data and transmits it to the target terminal. Alternatively, you could use space-time coding approaches, meaning this terminal, which is the source terminal, transmits its data to the target terminal, or may not, but important is that the relay picks up what has been transmitted, and then both of them form a space-time code word and send this data in a distributed fashion, which I've shown here by these two different colors. Now let's describe a little bit in more detail the channel-coded approach. And to this end, we will look at the outages. Now, the outages comes from the Shannon concept, but it holds very well for asymptotically large block lengths over slow fading channels, so it is quite a useful notion to look for the code design. And what happens here, and we follow here the paper 78 and 79, that each user tries to transmit a punctured incremental redundancy to its partner. We may use block or convolutional code, and we don't need any feedback because we assume decisions on erroneous transmissions have been done by means of a cyclic redundancy check. Now let me assume that I'm user 1 and you are user 2. Now I'm transmitting N1 bits. This is a broadcast signal that is being picked up by the target terminal, but also by you. If you receive my signal correctly, which you judge by means of a CRC, you would then build the redundancy, the parity data, and transmit in your second frame my data to the target terminal. Alternatively, you do exactly the same. Equivalently, you do exactly the same as I do. You encode your data, send N1 bits, which has been picked up by the target mobile terminal, but also by myself. And if I received your data correctly, I will insert in my second part of my frame your parity data. Okay, we have that. So my bits come here. I add the CRC. I have a rate compatible punctured code here. I'm puncturing out N1 bits and I'm transmitting them. And then I receive your data, which goes through the very same way. So I'm receiving your data, and if the CRC check says, all right, that data has been received correctly, I'm taking your N2 parity bits and I'm transmitting them in frame number 2. If, however, you received, for instance, my data erroneously, then you do not take my data in the frame 2, but you would just continue transmitting your own parity data. And I would do the very same if I received your case erroneously. So let us now look at these 4 cases here. So what can happen is that both of us receive each other's data correctly, meaning that in the first time slot we send each other's data, we send our own data, and in the second time slot we send each other's respective parity data. The second case which may happen is that both of us receive it erroneously, meaning in the first slot we send our own data, and in the second slot we send our own parity data. The third case is that I receive yours wrongly, but you receive my data correctly, and then of course you would resend my parity data and I would send my own parity data too. And the fourth case is exactly the opposite to the third case. So we have a radar code of length N1 plus N2, where we puncture N1 to be transmitted. So we define the rate alpha to be N1 over N1 plus N2. And we use CRC coding, CRC redundancy check. Now, how to calculate that outage here? And we follow here the Shannonian analysis, meaning for an instantaneous signal-to-noise ratio, the capacity of that link is given as C of gamma, which is a signal-to-noise ratio, log to 1 plus gamma. Now, the channel is defined to be an outage if the capacity falls or the supportable rate falls below a certain threshold R. And the corresponding event, of course, is given that C gamma, that one here, falls below R, or equivalently, if you rearrange that equation, that gamma falls below 2 to the power R minus 1, and therefore the outage is given by that probability expression here, which depends on the probability density function of the signal-to-noise ratio gamma. Assuming a Rayleigh fading process and normalization of the noise, we get gamma to be negative exponentially distributed, and we easily calculate 42 to be 43. Now let us look at case number 1, where I said both of us receive each other's data correctly, and if that happens, that means that the capacity from me to you must be bigger than the rate over alpha. Okay, so the capacity of that channel from me to you, log to 1 plus the signal-to-noise ratio between us two, must be bigger than rate over alpha. Equivalently, the capacity from you to me must also obey that equation. But that means if outage shall occur, that outage occurs if the sum of the rates from my data, my own data in the first slot to the base station, which is given here, plus the parity, my parity data, which you transmit, is smaller than the rate. And equivalently, for you it means that your own send data in frame 1 plus the parity data which I transmit for you is also smaller than the rate R. In a similar fashion, we can calculate cases 2, 3, and 4 simply by changing the signs here, here, and here. If we put it all together, and you can consult 79 here, you get the end-to-end outage probability, where the first case, as I've just described to you, is given right here. So you cater for the probability of our channels to be correct, which is right here and right here, and you cater for the probability that our respective channels to the target terminals are insufficient to support the rate, which is given here. And so you get all possible combinations in the end, and the performance clearly indicates where we show the outage probability versus the mean uplink signal to noise ratio. We show clearly if we don't use cooperation, we get a single gain performance here, whereas if you use a coded cooperation, we get a diversity gain here, which has a steeper slope. Now let's move on to the space-time code design, and following AT we assume that type of topology here. We have a source terminal, we have relay channel to the relay terminals, where we have K relay terminals which form a space-time code word and transmit that to the destination. We assume an MLSC detector at the destination, and what we're interested in is an upper bound to the pairwise error probability. Now, following paper 80, we know that at the destination we receive that vector here, where P2 is a power transmitted at the relay terminals, X is a space-time code sequence which the distributed terminals generate, DI is a diagonal matrix which reflects the relay state matrix, and H is a channel vector from the relays to the destination, and N is the noise. Now, the interesting thing is we look at the entries I. This I is either 1 or 0. It is 1 if the relay terminal has received the data from the source terminal correctly. And it would do that with a probability which is approximately at high signal to noise ratio 1 minus L multiplied by PK, where L is the length of the data frame and PK is the probability that an error occurs in the kth link, which is given right here with the variables explained down here. Now, if that has not been received correctly with probability L multiplied PK, then the entry is IK equates to 0 in the diagonal matrix, which is the state matrix. Therefore, IK will be Bernoulli distributed, which allows us to derive a few interesting insights. So let's derive now the maximum likelihood decoding probability that we do an error. So we try to get the PEP, the probability that I transmit X1 but receive X2, given channel state matrix I, a relay state matrix I, and channel realizations H, and that will be exactly the probability that the Euclidean distance will be for the sent signal will be for the received signal will be bigger than what had been sent, given these state matrices here. And in 8 it had been shown that you can actually upper bound that by this expression here, where I remind you that is a frame length, that is the probability that an error occurs in the kth link. We assume there are capital K relays here. The reason why that is not indices on small k is because we assume this symmetric scenario, and omega is given right here, where we have lambda in here, which are the non-zero eigenvalues of the send signal matrix corresponding to state I. Now that allows us to get a few insights on the design criteria, because if we look into the asymptotic regime, we can rearrange that equation in that fashion here, where we bring out the signal to noise ratio, and you see it has a diversity order of k here. So if we apply the diversity gain equation here, we assume d to be the limit for signal to noise ratio going to infinity of minus log PEP over log signal to noise ratio, and that is exactly k. So that indicates that any full rank MIMO code will really achieve full diversity, the full diversity being K here, the maximum we can do with that type of relay protocol. And I'm sorry, that should be the regenerative decode and forward space-time protocol. There's an error here. It's not amplify and forward. Now the coding gain is given as C equates 1 over... Pascal, c'est une tutoriel, je dois recorder. C'est un truc que tu dois faire? Parce que c'est une 30 minutes et chaque fois je dois refaire. Ça doit être avec zéro bruit. Tu dois faire des choses très longues. Ah, très bien, très bien. J'attends. Et je refais le slide. Ouais. C'est bon? C'est bon? Très bien. Merci. Following now reference 80, we can rewrite that pairwise error probability in this form here, where we took out the signal to noise ratio to the power minus k, and if we apply the diversity gain equation, being d equates to the limit of signal to noise ratio going to infinity of minus that the logarithm of that expression here divided by the logarithm of the signal to noise ratio introduced by same, we obtain k, which indicates that any full rank MIMO code will really achieve full diversity, meaning the full diversity being k here if the decode and forward protocol is used. I'm sorry, there's a mistake here. It should read decode and forward space-time protocol. Also, we can obtain from that equation the space-time coding gain, which is given with that equation 50 here. And that indicates that among all determinant maximizing space-time codes, we have to design special decode and forward codes which maximize the coding gain. The reason being because omega is within expression 50 here. Now let's have a look at the impact of correlation or at power assignment to the relays. And we follow paper 81 here, assuming a 2-hop system, again relay channels. But what we assume here is that each mobile terminal might be equipped with more than one antenna. Therefore, naturally, correlation will occur, and we would like to quantify its impact. It turns out that the bit error rate can be Chernoff upper bounded by that expression here, where we do have the signal to noise ratio here to the power m, where m is the total number of antenna elements in the relay stage. D min is the minimum Euclidean distance in the constellation diagram. N is the number of nearest neighbors. M is the, as I said already, the total number of elements in the relay stage. Now the interesting thing is beta deg, which is a degeneration factor, which incorporates the channel correlation. by means of the covariance matrix SK, which is incorporated into beta. Now, without going into further details, let me exemplify that. Assume we do have 4 antennas and we have the choice of distributing them. One way of doing it, we say, alright, let's give all 4 antennas to one terminal, meaning of course all 4 will be correlated. Alternatively, I could split it between 2 terminals, saying, okay, I'll give 2 antennas to one terminal and 2 antennas to another one. But if I do so, I need to decide how much power do I assign to each of these terminals to achieve the minimum bit error rate. Now you can expand for these 2 cases the degradation factor beta, and in the first case you get that equation here, and in the second case you get that equation here, where rho is the correlation factor and alpha 1 is the amount of power you assign to the relay, or equivalently it's the channel gain from relay 1. If we look at the performance graph now, and I depict here the degradation coefficient beta versus the correlation coefficient rho, we see that if we fix, for instance, a correlation of, let's say, 60%, we draw that line. I show the blue curve here being the 4 antenna case. That means my degradation goes up if I have just one terminal of 4 antennas like that. And if I have 2 antennas and I assign unequal power, or the channels are of unequal power, then it is this curve here. And if it is of equal power, it will give us that curve here. Now what does it show us? It shows that correlation has a bigger impact on the degradation. Okay, so that increase here is significantly higher. In fact, it comes from down here. This increase in degradation is much higher if I have these antennas all spaced together, as if I used 2 different terminals, but I did a mistake in the power allocation because the channels are not well balanced. So that is the message of that paper. Now let's look at the asynchronous protocol design now, and that is a quite recent area and a quite interesting and important area. And if we look at the methods which one can use to synchronize our distributed space-time coding system, you will see that we have a natural way of using the synchronization. We have an extended cyclic prefix way in the context of OFDM, and we also can use really designed asynchronous space-time coding methods. Let me now go into details for all these 3 synchronization methods. For the natural synchronization, assume we have a source terminal communicating with the target mobile terminal, and it would use 2 relay mobile terminals. Now the best case one can happen is that these relay mobile terminals are on the line between these 2 terminals, and therefore no matter where you place them, the signal it takes to travel, the time the signal takes to travel from here to here will be the same as from here to the second relay mobile terminal and to here, given that the processing time in each of the terminals is more or less the same. The worst case which can happen is if you have that one here on the shooting line and another terminal being displaced by a distance delta d. And we would like to quantify what is the maximum allowable distance delta d, so that you still have a form of natural synchronization. And of course, you would tolerate a certain delay as long as the delay in chips or in the delay is below the chip duration or below the sampling duration of your signal, and that can be easily calculated if you assume the source and the target terminal to be in the foci of the ellipse, and you would like to calculate simply the time it takes to travel from here to here minus the time it takes to travel from here to here, and you obtain the allowable distance delta d. And in fact, this is exactly what you do using these equations here, and you end up with equation 55, which tells you delta d has to be smaller than this expression here, where delta t is the sampling time or the chip rate, C is the speed of light, D is the distance between the target, the source, and the first relay mobile terminal. Now if we plot it here, for instance, I've shown here the allowed spatial separation delta D versus the distance D between the source and the first relay, and using, for instance, UMTS, which has a chip rate multiplied by speed of light of 75 meters, and we say, all right, let's fix a 50 meters distance between source and the first relay, which is on the shooting line, then we know that the other terminal can be displaced of up to more than 70 meters, which gives you quite some freedom in the spatial topology. Now, if natural synchronization is not sufficient, what you could do is also a CDD OFDM inherent type of synchronization, where CDD and DD has been introduced by Armin Wittmann and Armin Dammann and Stefan Kaiser in 1993 and 2001, respectively. It makes basically the channel more frequency selective by delaying the output of one of the or several of the transmit antennas. You don't need to change anything at the receiving side, but you gain if you use strong channel coders or equivalently MLSE on MMSE equalizers. What does it mean if you have your distributed arrangement here and one of the terminals transmits, for instance, its signal at a certain time moment, creating a power delay profile at the target terminal of that shape here, and the other one is slightly delayed because of processing delay or because simply he's spatially displaced, and you see he generates something which is slightly delayed here. Now, as long as the cyclic prefix is longer than the total delay of these two responses, my target receiver will very well receive a good copy of the distributed relayed signal. Asynchronous space-time code protocols have emerged recently, in particular 82 till 90 and also in 80, and we will concentrate on 80. And what happens here is we do have a source terminal communicating with the destination via K relays. We assume relay channel, assume that the source communicates during duration T, and then each of the relays, instead of transmitting at the same time, contracts that signal and transmits during a time duration T divided by K. Of course, like this, you avoid the synchronization problems on a symbol or chip level, but you have a much looser synchronization on frame level. And the question is, how do I construct an optimum space-time code word which maximizes performance for that type of configuration? And following 80, we know that at the kth relay stage, we would receive a signal which is given by equation 56, where S is the transmitted signal sequence, H1K is a channel from the source to the kth relay, P1 is a transmission power of the source, and N is the noise. Now we assume that, as I said before, the kth relay performs a so-called sequence contractions by means of a linear transformation Tk. So it receives a sequence vector Yk given up here and applies a contraction Tk. And we assume for subsequent analysis that we stack them all together, these contractions, into a code word vector X, which is defined like that, where T, capital T, is a K by K linear transformation. Now, assuming maximum likelihood decoder, the pairwise error probability can be upper bounded by that expression here, and I will not go into great details. The only thing which is interesting to see is if the diversity gain using the same expression as before is given as the minimum rung of the diagonal of these code word matrix XMXJ, meaning to get a good diversity order, you need to this difference matrix needs to be a full rank for any code word X, and therefore the tricky issue is how to design it, and therefore the tricky issue is really how to choose an optimum contraction matrix capital T. For your information, the coding gain is given for that equation 61 here, which also requires full rankness. Now, using the analysis in 80 and using some optimum Vandermonde matrices C, we obtain quite interesting results here, and I depict here the bit error rate versus the signal to noise ratio per time slot. And you can see a reference. We have an Synchronous protocol, the green one, the lower bound here, synchronous protocol with no delay at all. We do have a synchronous spacetime code with a delay of 60% of the slot duration, and you see that performs pretty badly because it is not designed to work in these conditions. And we do have the asynchronous spacetime code where the delay is less than the slot duration, and you see it behaves very well, almost as good as a synchronous one with no delay. Now that finishes the section on the regenerative physical layer design, and we will move on now to the medium access control and cross-layer design issues.